Good evening, Piyush sir.
Good evening, madam.
Sir, we wait for 2-3 minutes and then we will start the session.
Okay, no worry, madam.
Good evening, all. On behalf of organizing committee, I welcome you all on today's FDP session. Today, we have with us Dr. Piyush Modi sir. He is a chemical engineer with 12 plus year of combined industry and academic experience, specializing in extraction technologies, essential oil R&D, process engineering, and business development. He currently serves as Business Development Manager at Mamco Naturals Private Limited, Plant Lipids Group, where he leads multi-state operations and drives strategic growth initiatives. Previously, Dr. Piyush Modi sir held key roles as R&D manager, process engineer, and technical manager with hands-on experience in plant material extraction, process scale-up from lab to pilot scale, PFD and P&ID development, and pilot plant equipment design. He also served as assistant professor and head of the chemical engineering department for 7 years, contributing significantly to teaching and academic leadership. Dr. Modi holds a PhD in chemical engineering from SVNIT Surat and has published extensively in high impact international journals, conferences, and a recent elsewhere book chapter in 2025 on cinnamon oil extraction technologies. His research interests include green extraction methods, process intensification, and sustainable chemical processing. I request Dr. Priyesh Modi sir to start today's session for the FTP. Welcome, sir.
Yeah, thank you, ma'am. Thank you for inviting me. All of participants also welcome and good evening. So, should I start from presentation?
Yes, sir. Yes.
Yeah. Okay. So, everyone, can I see that window?
Yes, sir. It is visible.
Yeah. So, today's topic is extraction of phytochemicals from plants material. Okay. So, basically, we are focusing that. Yeah. how it's- Yeah. So we are focusing right now in that introduction of phytochemicals. What are the phytochemicals known? There is a different methods, which is conventional method and advanced extraction method. In that subparts also we learn. And one of the case study, which is cinnamon oil, how to extract the cinnamon oil from cinnamon bark. Also the case study of hydrodistillation, sono-hydrodistillation, microwave assistant. There are three methods we have studied, and then comparison that how we conclude that methods. And the major challenges in food processing industry nowadays, what happen in current market, that we have learned. And after all, we see the market review. So these are my outlines of this presentation. So basically, we are starting from the phytochemicals, which is known that natural occurs bio
Excuse
compound.
me, sir.
Yeah, yeah, please.
The PPT is not in presentation mode, sir. Only the title slide is visible to us.
Oh, now it's
You have to share, present your entire screen. Then
Yes.
only it is visible.
Yeah. Now it's okay.
Yes, sir.
Okay. So now visible to all of you?
Yes, sir. Now it is okay.
Yeah. Yeah. Thank you. So these are the outlines we already discussed, and so we start from the phytochemicals. In current market, there is a chemicals are available, which is the substitute of natural occurs only. So this phytochemical not used to in our day house, but the like not protein, vitamins, but it's promoting our health and preventing the disease. So basically, it's their colors, flavor, aroma, and this type of mechanism is known as a phytochemicals. So it is used in food, pharma, nutraceutical, cosmetic industry. That are the very vast use in the industry as a antioxidant, antimicrobial, anti-inflammatory, and functional property. So how they extract? So which of the plants part like leaves, some of the leaves of that plants, fruits, seeds, bark, roots and flowers we have extract from that. It is as a physical chemical advanced extraction techniques over there. So we learn about that techniques. What is important? So the importance of phytochemicals are act as a natural antioxidants and preservatives. So nowadays the we increase the shelf life of that particular food material. So we use the preservative. So if we are not using the synthetic one, we use the natural antioxidant. Like I say the example of rosemary. Okay, so rosemary oil is used for as an antioxidant and the preservative also. uh, it enhance the flavor and aroma of the food product. So whenever we taste the soup, okay, different type of soup we have used, like very well known company Nor. So they are using that type of component. So in that, so they increase the aroma and the flavor for the particular food ingredients. To support the clean label and natural ingredients trend, nowadays use very much in this type of ingredients in market. So it's offer our health benefits such as immunity booster. You know very well that curcumin, it is extracted from the turmeric. You know it's our very well known kitchen ingredients. The haldi we know as in Hindi, that turmeric. So in that the curcumin is a base immunity booster, and nowadays in winter season also we take up with the milk. So this type of phytochemicals are used as a health benefits, and it's provide the functional alternatives to against the synthetic one. Yeah. The major example of the phytochemicals: alkaloids, flavonoids, terpenoids, phenolic compounds like phenolic acids and glucosides. So these are the major phytochemicals which is available in different parts of the plant material. So basically, we are study right now that two I said that conventional and we can also say the non-conventional, but is it advanced extraction method? So right now we discuss about the conventional method. There is a four type of conventional method, which is maceration process, exoxylate extraction, hydrodistillation, and steam distillation. So basic we study about what is the maceration process. It is the very common method, which is a traditional method. You can say that it's a solid liquid extraction techniques. Okay, which is what happen. We are doing like soaking in any suitable solvent in a room temperature and dissolve that overnight of that particular plant material or phytochemicals. So we extract that, come out that phytochemicals outer layer, and we collect them, and we know as a that maceration process. So in our common example, like we are overnight soaking almond, you know that we are soaking that almond and we early morning we take up it. So the you see that the that water means of the which water we soaking the almond, they have the color will be also change, and some phytochemicals nutrients also coming out in water, so we can take up that water. So it's health benefits like same fig, okay, and almond or whatever. Another very much example over there, some of that overnight soaking cumin also. So these are the basic process, is a mercerization process. It's overnight soaking, nothing else, but it's a long time, means hours and days are going on that process. So which is the key characteristic? It's simple and low cost techniques, not so much equipment available required for that. So and operates at ambient and mild temperature. It is not required any pressure or any temperature. Suitable for the heat sensitive phytochemicals, means which is the degrade on the particular temperature sensitive for phytochemicals which available for that this method. So I already tell that it's long and extraction time, it's hours and days maybe. Some of the plant material soaking 2 days to means like 48 hours or something, 36 hour maybe. So what is the process step? I already explained that first we have to raw material preparation. So in that we require only the drying raw material, because whenever the material is dry, then and then it's happen the extraction. Otherwise, it not solutes are come from the solvents. So drying and size reduction. So when we required size reduction due to the amorphous area is increased, so the extraction, so oil gland will be rupture and the oil will come out. So we get the more phytochemicals from that. Increase the surface area, yeah, for the size reduction. And soaking, it's known as a mercerization process. So plant material emerge in a solvent, like we can also use that in that different solvent like ethanol, hydrolyc solvents, okay, hydrophilic solvent also we can use for the, it's suitable for the plant material, which plant material we do, okay. So extraction occurs by diffusion and osmosis process. You very well known about it. The techniques, agitation. Some of the dental agitation will be required for the better mass transfer operation. Uh, then after, if the process is complete, like after 10 hours, 12 hours, or whatever we decide that on basis of the optimization. So that after that the completion of the extraction, the solid residue remove and extract all the collected. Some of that solvent, the solvent are we recover the solvent, and if not we require, so we remove, like rose water, okay, we, if we soaking rose petals over a night, so we use the direct rose water as a final product, not required to remove that water, okay. So what is advantage and limitation? So minimal equipment requirement, low energy consumption, suitable for the small scale and traditional process, preserve thermobaric compounds, because it is not heat sensitive or no any pressure, any temperature. So it's very much popular for that those type of compound. Limitation. Another is the time consuming process, lower extraction efficiency. Yeah, maybe it's some not properly extracted from the plants. Any phytochemicals may be possible. Larger solvent requirement because we have to soak the material. So it's, you know, that the ratio may be 1:5 or 1:10 sometimes. So it's larger solvent requirement. Limited scalability for the industrial production. It's not very popular for the industry process. Solvent extraction. So in that the continuous solid liquid extraction techniques, it's used as isolated phytochemicals from the plant material to hot solvent reflux. So we continues circulating that solvent. So from that come out the oil from the oil gland, and that collect from the oil, and circulate are separate. Key characteristics. The continuous and extraction operates the boiling point temperature, high extraction efficiency, time and solvent intensives. So in this process, that process steps are, uh, at first we have to just every process we have to do some moisture removal due to the higher efficiency and grinding of that plant material. So it is a size reduction. Then we add thimble, which is the operate in equipment is known as a thimble, which provide a filter paper. So not plant material are not come out from the in our particular main part. So solvent thimble we have to add a filter paper, solvent heating, uh, which is different type of solvent used like hexane, ethanol, and etc. So and then after the condense that solvent, so vapor are come out and drip into extraction chamber. Now that siphoning is the continues over around in that Soxhlet apparatus, then the after that we have to solvent recovery will be most possible for the, so ppm level the extraction is required, means solvent recovery is required, otherwise it's health conscious component. So we have to remove at ppm level. Majorly in industry there is a below the 10 ppm we require for the any type of oil extraction. So this process also advantage and limitation. So simple and reproducible techniques are there. High recovery target. Yeah, in that particular we can also target the particular component. Like if the cumin is there, so we can target it cuminaldehyde for the particular component. So this possible in this oxalate extraction. Suitable reference and benchmark method of that available in means known as this oxalate extraction, and well established in laboratory. We can means first we check the raw material how much content of oil available. So every industry are use this oxalate extraction method, so it is well established in that laboratory only. The means low capacity 1 liter 2 liter processing capacity, and limitation that long extraction time, it's circulation of like 7 to 8 circulation, so it requires 6 to 24 hours maybe. And high solvent and energy consumption, not suitable for the heat sensitive, because we the solvent temperature is very high then, and then it circulates among the thimble. And limited industrial scalability. Now it's a very popular and known method, which is hydrodistillation. Everyone may be seen in this method in anywhere. Like we go for the Uti for eucalyptus oil. You know that it's they are soaking the eucalyptus leaves in the water, and they just heat the water, and from the boiling of the water they collect the uh, oil and water come out from the top, and we separate the condenser, and then water and oil are separate, so we collect the oil. So that is a simple hydrodistillation method available anywhere. We can put the setup of that particular matter. So in that volatile oil component from the vaporize with steam and recover by the condensation. And after that we already I discussed that oil and water are basically separate by gravity, so phase separation will be there. So we collect the oil. Its key characteristic: direct contact of plant material with boiling water, operates at atmosphere pressure, not require any pressure, suitable for the robust plant materials. Like any plant material we can do that this method, and simple and low cost method for particular plant material. So in there's also process steps, fresh and dry plant material also we can do. We are not required in that remove the moisture, which we discuss in maceration and so oxalate method. They require dry product, but in that we can also use the for some of moisture product, because already we added the water. Charging that distillation unit, that we add the material and water together in that, and make and heated the water, so we come out that vaporization. So oil volatile components are come out from the top with the steam. Then after we condense it, yeah, and after that we separate that material, and we collect that this, yeah, one of that hydrosol collected by the last point is the very important. It is a byproduct. I already say that rose water. Okay, so whenever we extract the rose oil, okay, so the oil is collected from the top, okay, with steam. So by the separation of gravity separation, we phase separation we have conducted, so remaining water, okay, below that oil. So it is very much popular as a byproduct, and it's already sold in market. Every component, like means it's like merry-go-round or jasmine or wherever, whichever fragrance base, they are also using hydrosol. So it's known as a means very popular byproduct, hydrosol. The oil and hydrosol we collect in every flowers material extraction process. So some of advantage and disadvantage, the like limitations of that hydrodistillation extraction. Simple equipment, it's easy operational. Well, no organic solvent, clean process will be there. So suitable for small and traditional process. Wide exception in food and flavor industry. Uh, Not suitable for heat sensitive, because we extract the plant materials for the particular, we come out that molecule will be degrade of that particular phytochemicals. So do not require like below above 100 degrees Celsius of temperature. Possible hydrosol and degradation of some component, lower oil quality compared to steam distillation. We study that steam distillation also uh, longer process time. Sorry, I disturbed. Steam distillation. It's widely used in essential oil extraction techniques in which steam pass through the plant material. Same phenomena in that, but we are not submerged that water or anything, any solvent. Only the plant material is situated, located over there, a platform, and we pour the steam below the material. As the steam has passed to the plant materials, and it's break up the oil gland and collect and carry the oil gland oil and with steam at the top. And then same in hydrodistillation, we collect the uh, vapor and oil, water, then after we phase separation. So no direct contact between plant material and boiling water. So only the steam will be touch that plant material. Operates at low at temperature below the normal boiling point. Reserve oil quality better than hydrodistillation. Highly scalable in industrial acceptance. Yeah, most widely used that both one steam distillation and hydrodistillation. So same process step as per we see that in uh, hydrodistillation, that in that we use that fresh material and dry plant material, we can both we use in that. Only the required that we in that we high pressure steam coming from the boiler or anywhere. So from that we uh, impulse to the from the bottom of that plant material, that then after we extract that in distillation unit. So the steam will be come out from the top, and we condense that and separate, and we collect that product. So steam distillation advantage is simple and reproducible techniques, high recovery and targeted component, suitable method. Limitation is long extraction time. It's also consuming long, because in very first circulation of steam, they are not coming all plant material, oil gland from that rupture the oil gland and come out the oil. So it's long process. So for this limitation, we omit the we to develop some advanced extraction techniques, so that whichever the limitation, like long time, okay, and the different solvent, maybe ppm level remove will be not possible. So we develop that this type of method in advanced extraction techniques. It's known as like ultra assisted extraction, microwave assistant extractant, supercritical fluid SCFE, and pressure liquid extraction. So in an ultrasound assistant extraction, it's work on a basic principle of that hertz, the wave we have developed, and from the wave and through the wave, the rupture the plant cell and improve the mass transfer from the cell wall, and we collect that oil, and uh, mm, that after that same process we condense the oil and collect the material. So it's operate at low and moderate temperature. Both we can do short extraction time, because in limitation means we limited time we can extract that material, because the disturbs of the plant material is very rare in that particular method. So the yield is very high in that ultrasound assistant extractor. Reduce the solvent consumption. So we require minimum solution, which is used in mercerization process. Very high solvent. It is not. Its ratio is like 1:2, 1:1, 1:1 maybe. That like that, not higher ratio of solvent use. Uh, High extraction efficiency for particular process. So principle is that ultrasonic wave is generated and that micro bubbles are ruptured in particular plant near to plant material, and is create the high pressure. So that plant wall will be uh, break and come out the from the oil clean, and extract that material, like enhance the solvent penetration and faster extraction. So in this process, we require dry material. So we have to extract more and get the more efficiency. And yeah, of course, this size reduction also required, because the if this area of increase particular plant material, so we very well rupture that plant material, plant cell and membrane, and from the cell membrane to extract the oil clean. Solvent addition, we can use the ethanol, right? Some hexane, whatever suitable solvent also we can use, but most probably we are using water as a solvent. And ultrasonic treatment, they apply the probe, that like there is a different hertz probe available in market. So we use that probe and rupture that plant material. Then after we separate that solid particular solids, means like plant material and the room which available in oil recovery. And then after we also solvent recovery in that particular, if we use the solvent, then otherwise most probably use the water only. Ultrasound its advantage is the heat, it's suitable for the heat sensitive because you're not getting high temperature over here. Only the mechanical rupture is there. So whenever the required, there is a phytomolecules are very heat sensitive, that some of the are not required to below, means above 100 degree temperature, it's degrade. So that type of phytochemicals require this method. Energy efficient and environmentally friendly, because there is no any type of harm. Only the noise pollution is there, but no, it's under the decimal, so no worry about it. Higher yield compared to the mercerization and software. Yeah, easy interaction with existing process. Limitation are the depth and large volume that equipment cost is higher. So second point is very important for the industry also, because that's why only the lower capacity equipment available in market. So not it's required the means available in large scale. Next method is a microwave assistant extraction. So in that microwave extraction assistant, there is a 300 megahertz to 300 gigahertz energy wave penetrate over there. So it's planted rapidly and enhance the release the phytochemicals particular, which are very popular method. It's directly penetrate the component oil gland, not targeted to any solvent or any substance. It directly targeted to our oil gland of the plant material, then come out that oil and we collect that oil material. So it's a very short extraction times, like in minutes we can achieve. The very well the what is the role of microwave. Okay, in this in your kitchen also, in very few minutes they heat uh, our food. Any type of you know the very well what is the process of pizza making. Okay, so its high extraction efficiency, reduce the solvent uses. If so required 1:1 or 1:2 only solvent ratio. Uh, precise control of temperature. Yeah, you can control easily here the temperature and time due to that control available in the panel. So what is the principle that that very polar molecule only the penetrate that heat waves and then heat up that material and its dipole rotation of the particular component, then and then it's increase the energy and heat will be generated. So that pressure will build up in the plant cell and then rupture the plant cell and release the intermolecule like oil. They improve the mass transfer and reduction the extraction time. In this also we require drying of the plant material, then size reduction, same over there. Solvent addition, we can add water, ethanol, anything from that. And microwave heating is energy applied to open system and closed system. Both we apply over here, and it's rapidly heating the plant. In a minutes, we can if we put plant material within a 3 minutes, within a 2 minutes, the result will be come out from that plant material. So it is the release that phytochemicals or oils in the system. Then after we filtrate the material and remove the solids, and also we require the if we add the solvent, then we require the solvent recovery. So advantage is a suitable heat sensitive and thermomobility compound, higher yields, the maceration and chocolate, energy efficient. Yeah, we can say that energy efficient. That the its energy is very much huge use, but it's a fraction of time, like or low minutes or seconds the yeah, run. So the energy is very much low in use. So like we can also use for a green solvents in that. Limitation require polar solvents only is they work in a polar solvent. You know very well that polar and non-polar. So equipment cost is higher than conventional. Yeah, hydrodistillation and steam distillation are low cost equipment, but it is a sum of higher risks for the thermal degradation if the parameter are not controlled. Yeah, temperature, some of time the temperature is very high, running over than if you set the higher time. So we have to control the time and temperature in that method. Scale up is complexity, but running in the lower capacity is available in industrial scale. The next very popular nowadays this method is the supercritical fluid extraction. So supercritical fluid extraction is advanced grain extraction technology because in that there is a no hexane, no ethanol, no any hazardous chemical solvents will be used. So it is used in the supercritical CO2 only. So CO2 we can remove easily, and so from many industry are prefer this type of process, and in that the yield is also higher, but the only the things they are the come out all composition of the plant material. Yeah. So key characteristics: solvent-free final product with low operating temperature because it's high pressure and low temperature operating processor. Yeah, temperature is very high in that process. Highly selective extraction we can do only. We are not doing like eucalypt soil and everything in this process because it's not viable for the particular process. That's why only the reason is there. Yeah, environmentally friendly process because not harm any solvents or anything. So that's why. Yeah, on principle is that both gas like diffusivity and liquid like solvent thing power that is the main CO2. That characteristics of that. So it penetrate the plant matrix and come out that through the pressure and temperature. It's come out that plant materials oil gland rupture the oil gland and come out that oil, and that after the separate the CO2 and the oil. In this they are using that size, yeah, for it reduce the plant material size and pour the in cylinder of the particular, and they operate 70 to par around and 31 degrees celsius may be critical point of that particular CO2. Then extraction vessel, we fill up it with that and target the phytochemicals that come out from in through In that hydrodistillation and steam distillation, we come out and with the steam. In that come out with the CO2, and then after CO2 recompress, and you separate that oil, and CO2 will be reused for the again for the second cycle. Yeah, supercritical, that advantage is no toxic solvent. We already discussed of that, and preserve thermomobile compound, high purity extract, easy solvent recovery and reuse, widely accepted in food and pharma industry are very much acquire that this type of plant material oil in like ginger oil very much demanding of the only CO2 based extraction is possible, so it's very much demanding in ginger oil in CO2 process. Limitation highly capable and operating cost is very much high because we have to maintain CO2 is very complex. That equipment is also if available in sorry I can't attach that equipment. Okay, but it's very complex equipment because you have to maintain the higher pressure bar, limited polarity over that uh, required for the solve. So last method is that pressurized liquid extraction. So in that advanced extraction techniques, the solvent are elevated with the temperature and pressure both. We elevate so that the phytochemical, which is the not heat sensitive material, so we can use that this method. It is a short time extraction method and lower solvent consumption, high reproducibility and automate operated possible. In principle, that solute the solubility and mass transfer, keep solvent in liquid phase above its boiling point, so we increase the temperature, so it's reduce the solvent viscosity, improves penetrate to the plant matrix, and that come out that oil from the oil gland. And in this also the steps are first with drying and grinding, that due to the size reduction of the plant material, that loading that particular vessel. We most probably use that SS stainless steel because all of certain oils are acidic. So like I say about the rosemary oil, so it is also some of the acidic arsenic acid is available in that composition. So most probably all of essential oil are used for the use in a SS vessel only. Yeah. So solvent pressurized that we use that solvent ethanol hexane and it's pumped to the high pressure pump, and so we create that temperature also is 200 up to 200 degrees Celsius, and also pressure will be applied. So after flush and purge, both we use that nitrogen due to required for the residual solvent recovery means and the particular pressure for this process. And after if we use the hexane or ethanol, we reduce the recovery is required in the particular process. Pressurized liquid extraction advantage is the it's a very fast process against the conventional both Soxhlet and maceration process, suitable for wide range of phytochemicals, which is not only the heat sensible. Good extraction efficiency, compatible with green solvent. Limitations, it's high equipment cost because the high pressure pump required, temperature also we elevate, so it's required thermal degradation possible for the already discussed. Limited to industrial scale absorption and reduced requires only the skill operation. Manpower also required very good in this process. Yeah. So we discuss all primary methods, okay, conventional or advanced, both method we discuss. Now we take one case study, so you realize that how its methods are work for the particular plant material. So I have take that one of the cinnamon oil, okay, which is extract from the cinnamon bark. Okay, so I also explain what is the cinnamon and what is the cinnamaldehyde, which is the major component in the cinnamon oil. So we check with the traditional method, which is a very popular well-known method is hydrodistillation, and against that advanced method, microwave assistance and sono-hydrodistillation. So sono-hydrodistillation I work from as a ultrasound, you know very well. I already explained on that. It's probe is there, so on basis of that waves we create ultrasonic wave and rupture the plant material. So those three methods we compare over there and we create that comparison. Yeah. So what is a cinnamon? It's a plant material. Cinnamon xylocinum is a botanical name. Its family is from that, and it's used in spice, syrup, mouth freshener, you know, flavoring material like. So originally it's native is South India and more probably in Sri Lanka. It's very popular for the true Ceylon, and we in kitchen we known as a dalchini. It's a reddish brown sticks type of material. Its application in food industry, fragrance and flavor, pharmaceutical industry, antibiotic, antioxidant, antimicrobial, anti-cancerous study. Uh, Also used in cosmetic industry and perfumery industry. So, if I've taken the cinnamon plant, so there is a different composition available in different parts of plant. In very first column, you see that the leaves, bark, root bark, both are different, like birds, flower, and fruits. So these are the plants part of that particular cinnamon, but we use only the bark because what happened we have I have targeted component of cinnamaldehyde which is used very popular for the phyto industries and pharma base also. So you can see in this table one of the uh, good things that leaves there is a eugenol component is 70 to 95 percentage, but at the same time you can see in bar only the 1 to 4 percentage. So you see the study that every plant materials different part have a different phytochemicals, not even only this plant but some of the other plant also this type of phenomena happen in it. Some of the few only 10 percentage it is a one of the dead, so I have which I select. So leaves we only the study are very totally different and the bark study is totally different. Yeah, because so this extracted component from the oil, it's cinnamaldehyde, which is major available in 65 to 95 percentage. So it's known as a cinnamaldehyde. It's pale yellow liquids and warm and sweet and pungent, which you in your kitchen you already taste that cinnamon. Okay, so its pungency is due to the only this cinnamaldehyde component, otherwise another part is only the cell structure, nothing else. So this medicative properties are also good, so that's why they use very popular use in cinnamon in our kitchen also. Yeah, application of the cinnamon lower cholesterol, reduce blood sugar level, heart disease, fight against cancer, mouth freshener, brain tonic, and infections. So this is the extraction process diagram. Okay, first we take the cinnamon sticks. We already discussed the process step, which first we have to grind. So the size reduction is a very must required in any process because we can't do the direct sticks. Okay, if we can do the powder. Okay, and powder is also not like a very low mass size powder like talcum powder is some amorphous material. So we can get the better enhance of the bus transfer operation. And then after we use that any of the method which is I have shown that conventional and non-conventional which is advanced method, we get the oil and then we do the GC or GCMS of that oil and we find out that how much component available in cinnamaldehyde in that oil. So I select that hydrodistillation. These are the setup. You can see that this experimental setup of the 5 liter capacity of heating mantle and the 3 of that flax. So we have used that solid loading is 20 gram material, average particle size is 100 micrometer, and extraction time is 120 minutes. Heating power 500-watt heater is there. So we apply the 400% power over here, and we had a 500 ml of water only because the ratio we maintain over there. Then after the same, you can see that the sono hydrodistillation extraction SHD, you know that it's you see that SS probe is penetrated over the flask, so it's rupture that and waves are created, ultrasonic waves are created. So in that, one of the parameter is amplitude. So 30 to 60% amplitude will be the range I have studied over there, and pulse ratio 10s to 50 and 40s to 20. It's on off cycle. We know continuously on the probe. We just put stop and on. So it's then and then it's burst the bubble and rupture the plant material. So you can see that setup of that ultra sonohydro distillation extraction. Yeah. After that extraction, how you appear? It is the most important slide of that. You can see that first a figure. It is a fresh cinnamon bark. Okay, which of you see that full of oil contain all of oil gland are there. Okay. Then after we apply that method sonohydro distillation, so it's rupture that plant material and it's burst the plant. Okay, so you see that it's all holes are empty. Okay, so same same plant material I have studied after that. So it is no symmetry microscopic study for the particular plant material. So in that we get the 4.64 percentage weight by weight yield of that cinnamon oil, and the cinnamaldehyde is a 0.94. The optimum time is 20 minutes, 60% amplitude, 500-watt heating, because both we also run the heating mental power and the ultrasonic both. 25 to 35-second pulse ratio also in that. So we get that oil in this. We can see that result of that SHD techniques. Okay. So next we study that microwave assistant extraction. So in that there is again it is a small setup which is available in our lab. So I have study on that. So its solid loading is 20 to 40 gram. Okay, soaking time 5 to 15 minutes only. Extraction time 30 to 60 minutes. Only in I have studied half an hour to 1 hour on plant material extraction time, and microwave power is 300 to 800 watt. Uh, Volume of water is 100 to 750 ml. So in that we get the result of 4.83. In that I also add one thing that you not increase the water volume in particular, because if you increase the water volume, okay, your plant material is come out from the flax, because it's rapidly increase the temperature. In sudden 1 minute you can rise the temperature of that up to 100 degrees. Okay, so we also optimize the water volume in here. So optimized parameter is the 12 minutes, so 50 minutes extraction time, 12 minutes is soaking time, 50 minutes extraction time, and 30 gram solid loading and 800 microwave power here. Okay, so we get the yield is 4.83 percentage and the cinnamaldehyde is 0.92 fractions. So I have studied three methods, so you can see that result. Okay, how we get, so you can see that here result 3.23 percentage of yield in hydrodistillation. This is the sono hydrodistillation, 4.64 percentage yield, and the microwave assistant it's 4.83 percentage. you can see that its yield is very high in microwave, but the fraction of that is 0.92, and here the sono listen the fraction is 94, because the here we use the mechanism of ultrasonic wave, so the rupture the blunt metal by mechanics, and here we use the penetrated dipole moment through the water, so here that temperature we increase, so that is maybe the reason to increase that 0.02%, not notable only the okay. So these are the results, so these are the conclusion we already we discussed. And after extraction the waste are used in bio pesticides also, so and and this essential oil market are very growing in nowadays globally. But some challenges are also in our industry, okay, because it's no, you know that it's a natural product, so it's depend on the agriculture. So the supply, poor supply chain in particular raw material only, infrastructure bottleneck, no are FBD available in every town, or the transportation issue, railway, airways, no everywhere is over there, unskilled manpower, so the farming industry are not grow up on the particular pro that unskilled manpower for that this industry, quality also degrade because that the high market competitive and limited the export material, low level of processing certain sector, because not directly process that immediately process at seasonable crop is there, so it is require higher pungency over there. uh, and regulatory environment also in particular process, that challenges to acceptance of natural food products, its price preparation, because due to the supply chain there is a price gap is also over there, depending on the seasonable crop. Unfamiliarity with ingredients, taste and texture concern. Yeah, so you see in that basil oil. Okay, there is a 12 type of crop of basil. Okay, so different basil has a, like its major component methyl charcoal is there. So every crop has a different percentage. So every basil oil taste profile and aroma and fragrance, all are different, so you also depend on that particular crop, not another is a quality inconsistency due to the weather and the natural circumstances, that's why limitation to availability, some of the crops are it's seasonable, so limited availability, only the season they available, labeling confusing, misleading and mishandling of that particular. So strategy to overcome that challenge is we have to educate and awareness campaigning, which is borne by the government or NGO something, organization will do transportable labeling, taste optimization. We have to also uh, coordinate with the particular industry, so we establish the profile and crop variety, quality standard, retail partnership, production even mission. Yeah, you know that CMAP and this type of institute of develop only their work on that essential oil crop and everything, CSIR activity also there, uh, the endorsement means advertising and marketing particular, and community engagement for the this awareness of that natural products. The essential oil market by country in North America, USA is the largest market. Canada also over there. Europe in France, Germany, UK. In Asia, China, India, and Japan. And South America, yeah, also Brazil. So these are the global essential oil market trend, which is the 11.8% CAGR. It is very growthable market nowadays. After the COVID, everyone required a natural one and natural products. So before we used the in a morning tea. Only we put up tulsi and mint, means pudina leaves in the particular our tea. But nowadays, some of use oil drops. So that oil drops not only it's essential oil only. Yeah. So thank you all of you to attend that this event, FDP. So
Thank you, sir.
any, yeah,
Participants, if you have any queries or questions, you can ask.
yeah,
Good evening, sir. Thank you very much for your nice lecture.
yeah,
I have a question. That is, I think there is a in the extraction technique, extraction of the phytochemicals,
yeah.
there is a possibility of oxidation or degradation. You mentioned there
Okay,
in most of the cases. In
yeah.
which process that oxidation possibility oxidation is minimum or less?
Oxidation, not possibility, but what happened? They are only concerned about the temperature and means uh, we thermal stability. You can say, okay, if some phytochemical like limonene, okay, flavonoids or alkaloids are there. So some of that higher boiler and some of that are lower boiler. Okay, so the higher boiler are not affected to the temperature, but the lower boiler are very much affected in the temperature, and that they are rotated in dipole moment. Okay, like that cis and trans. I give the example like cardamom oil. Okay, so cardamom oil have a component of 1,8 cinnamon. Okay, it is a major component which is the sweetness, pungency, and over there. So due to the only 1,8 cinnamon component, but it is available in cis form. Okay, but same way the eucalyptus oil is also there. It's also 1,8 cinnamon, but is a trans form. So that is a different will be in that particular very to very in component of plant material. So I can directly say that it's affect that oxidation of that. It's affect the thermal stability and that temperature effect only. Yes, sir.
Okay, okay. Actually, degradation it is it will it can be avoided or it will be less in which type of technique that is very difficult to say, right?
Yeah, degradation is the very typical, but most probably you follow the traditional method like hydrodistillation, okay, or you say that ultrasonic, okay, so it is not possible to degrade. But against that, you just see the which plant material you select, okay, so you know the how which parameter which composition is available and how much boiling point you extract the material. Okay, some of the plant material have initial some characteristics of evaporating that oil, VOC, volatile organic component, you know that. Yeah.
Okay, 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 okay.
Okay, sir. Yeah.
Okay.
Yes, any other question?
It is not a sorry, I have disturbed you, but essential oil in everywhere in our today day to day life, but we not recognize it is essential oil. Okay, that is the phenomena. Okay, we use as a spice only. Yeah, but ultimately we use as a essential oil when we spray the perfume in our body, so it's only the come from the natural molecule. Okay. Nowadays it is synthetic available also, but it's blend of natural, not totally synthetic one. Yeah. Please, any have any question you can ask. We have a time, like I think.
Yes. Participants, please ask your question. Yes, anyone has any query? Participants, you can ask query through chat box also. If anyone has query, question, please ask. Okay, it seems there is no questions from participants. So, sir, we conclude here. So, today's first session, we conclude here. On behalf of the organizing committee, I extend my sincere gratitude to our esteemed speaker, Dr. Piyush Modi, sir, for an informative and engaging session. Dr. Modi clearly explained the importance of phytochemicals and their applications in pharmaceutical and research field. He provided a comparative understanding of both conventional and advanced extraction methods, highlighting the advantage and disadvantage of each method. The case study on cinnamon oil extraction was particularly insightful, effectively linking theory and practical applications. He also discussed the major challenges faced by the food processing industry, along with the acceptance of natural products and effective strategies to overcome these challenges. We truly appreciate Dr. Modi's valuable time, expertise, and clarity of presentation, which make this session highly beneficial for all the participants. Once again, on behalf of the Vidyadeep Organizing Committee, I thank Dr. Piyush Modi sir for his meaningful contribution on this FTP. Thank you very much, sir. Hello, sir.
Yeah. Okay. Hello. Yeah.
Yes,
I'm
sir.
audible now? Yeah.
Yes, sir.
Okay. Thank you, madam, for
Yes,
your
sir.
invitation and participants. Have a nice day. Thank
Thank
you.
you, sir. Thank you. Participants, just wait for 5 minutes. Actually, our next session is start from 7:30. So I just ask the expert to join. If he is ready to join earlier, then we start our session. And one more announcement is that on your Atal FDP portal, where you applied for this FDP, your attendance and test link is generated. So kindly go through that. And if anyone has any query regarding attendance, so you just ping message on my WhatsApp number. Participants, please wait. I have just contacted the second speaker. Good evening, all. Our next expert is about to join, so be there. Welcome, sir. Sir, your mic is not on.
It's on now.
Huh. So, good evening, all. Again, on behalf of Vidyadeep University's organizing team, I welcome Dr. Anurag Gautam sir to today's session. Dr. Anurag Gautam sir is a professor and senior researcher with over 16 years of post PhD experience in material science, nanotechnology, and advanced functional materials. He holds a PhD in material science from IIT Kharagpur in 2018 and is currently serving as a professor R&D physics at Malla Reddy University, Hyderabad. Dr. Gautam has extensive international research experience, having worked as a postdoctoral researcher and senior scientist at leading institutions in Canada, USA, Sweden, and a senior consultant at Seed Nanotech International, Toronto. His research spans nanomaterials, energy storage, corrosion resistance material, solar cells, addi- additive manufacturing, and biomedical imaging, with a strong focus on MRI imaging and multimodal diagnostic applications using cyanide based nanoparticles. He has an exceptionally strong publication record with 30 plus papers in high impact international journals, including Coordination Chemistry Reviews, Journal of Energy Storage, Chemical Materials, and ACS Applied Materials and Interfaces, along with multiple book chapters published by Wiley and elsewhere. Dr. Gautam is also a recipient of multiple international postdoctoral fellowships and has delivered invited talks at premier national institutions, including BARC and OP Jindal University. Now, I request Sir to kindly proceed with today's session. Thank you.
So thank you, ma'am. Thank you so much. I'm coming back. So, can you see the screen now?
Yes, sir.
Okay, let me go full screen. Okay. So my talk is on lanthanide-based nanoparticle for the contrast imaging, mostly for cancer and tumor cells. So the title is Future of the Contrast Agent. Is possible to cure the cancer with lanthanide-based nanoparticle or any other nanoparticle such as gold nanoparticle. All are very useful in the uh, already from last decade. They are very useful and they are going to be very useful in near future too. So the idea is to how we can make it, because till now in India I assume we are not applying much as a nanoparticle. So this part of the work which I'm going to show, this is mostly done in Canada, because these nanoparticles were injected in mice model and then got imaged for the tumor cells, and we saw decent contrast. So we are going to use the lanthanide based nanoparticle, that is rare earth. Mostly the till now at a clinical stage, we are using the gadolinium based contrast agent, mostly complexes and chelates. At whenever a person go for MRI, let's say at very early stage, then from the normal tissue contrast to tumor contrast is very less. It's very hard to recognize whether its tumor is there or not. So for that, we need a contrast agent. If somebody is at a later stage of the life or later stage of the tumor part, let's say third stage, it is possible that you can visible from healthy cell to normal cell can be easily differentiated. But in the case of early stages, we do need this contrast agent to see the differences in them. So I'm now proceeding for my talk, what I have done there. So basically, when we are talking about MRI, so mostly you'll go like we say that MRI is a contrast agent. We use the field, magnetic resonance imaging, magnetic field. We apply the field. So two types of contrast agents are possible. As you see, I have already said here, two type contrast agents possible, either T1 or T2. When anybody goes for the diagnosis, the machine, they operate in T1 mode or T2 modes. So one is T1 based contrast, other is T2 based contrast. But this is all after injection of the nanoparticle or the contrast agent. So when we are saying longitudinal, when we are saying T1 based, so in that this is wrong. The molecule relax longitudinal way, and the contrast of the tissue compared to tumor tissue and the healthy tissue. So healthy tissue will be the darken, and the cancerous tissue will be whitening. If it is T1 based contrast, then we will get the whitening contrast. But if it is we are going T2 mode, then the with compared to the healthy tissue, the image will process for the tumor that will be darkened. It's called T2 contrast. And lots of parameters are there to see the differences. So we also said, like literature also said, that if R1 now these are for the contrast agent, we report as not at the time, we report as in the form of relaxivity. So that is inversely proportional to 1 by T normalized by the concentration of the compound. So we will say that R1 is proportional to 1 by T divided by the concentration of metal ion. So that is called relaxivity. So the contrast agents are reported in the form of relaxivity, not in the form of relaxation time. But relaxation time is very important, because shorter the relaxation time, high the relaxivity. If higher the relaxivity, more better contrast. Then a third parameter, if the and each contrast agent, whatever contrast we see, both has T1, T2. If you put any material in water, it will relax both the way, either T1 or T2 both way. So, but one is higher, either T1 is higher or T2 is higher, depending on the nature of the material, if it is paramagnetic or high magnetic. So, and also some other parameter that defined is T1 or T2 contrast agent. So for gadolinium, the one currently used at clinical level, it is a T1 based contrast agent. So for the tumor, it's produce whitening contrast compared to the normal tissue, whereas the dysprosium, that produce darkening contrast. So there are some ions that have been used in the past, paramagnetic compounds with large number of electrons, such as gadolinium, which has 7 unpaired electron, or Mn2 plus or iron 3 plus. They all have T1 contrast agent. So at present, at clinical level, we are, as I said in the beginning, we are using this GDTPA and some other complexes. And machine works in clinical level was earlier, I think couple of years back, it was 1.5 Tesla, but now MRI machine also operate at 3 Tesla. And animal model, they have already gone to 7 Tesla. So higher the magnetic field, better relaxation rate, better is the contrast. But they have gone 7 Tesla, they only went for the animal MRI. So the question now the question is that, so we are using at the clinical level gadolinium still, and FDA also approved iron oxide nanoparticle, because lots of iron parts, iron oxide and iron we have in body. So iron have been also approved for the MR imaging. But it is possible that some part of body you need specific. Why we are not going with iron research at the moment? Research is already approved by FDA, Food Drug Administration in America. They have approved iron oxide, but we are trying some other like lanthanide-based nanoparticle, because if you are going for multi-modal diagnosis, where we are saying a sort of injected nanoparticle can produce MR contrast, that can also produce optical imaging contrast. So we will see the contrast from the tissue in MR imaging, but we also can see optically, or other method can be also used. For that purpose, iron oxide or iron is not very suitable, because differences the size of the cation. So this rare earth based nanoparticle can be better in that respect. That's why we are trying, because iron oxide quenches the luminescence heavily, but this rare earth based tetrafluoride, they produce good imaging, optical imaging. So they can be used for that. So can the nanoparticle be the contrast for alternative for nanoparticle? So yes, it is certainly. So these are some methods. You all know that it's already that how we can synthesis of nanoparticle possible by top down or bottom up, depending how they're going. When we are saying the bottom up, we start from ions to atom to cluster to metal nanoparticle. But top down is more from bulk. We start from bigger particle and disintegrate into smaller particle. That's for ball milling, lithography, different purpose for that. So this paper, I think I did during my PhD work. And this is recently I published GML, General Molecular Liquid. It's good journal, impact factor 6 around. So earlier, like we are just saying that here image is showing that the nanoparticle can have different contrast, different optical emission at different size of the nanoparticle. This all well described. Even for gold, has different color: yellow, violet, blue, purple. All gold has color, but at nano scale. Bulk gold is yellow, which is often we know this is a bulk, like everyone knows bulk gold yellow. But gold also have this small size, different size. They have different colors, and they are very useful for biomarker application or the tagging, or many applications they can be used. So this is again, if we change the shape of the gold particle, if we change the shape here, so if they are shape of like capsule, 50 centimeter, the color can vary depending on aspect ratio. When we are saying aspect ratio, this is length by width. So if you tune this, the color will change this side. So here the aspect ratio is increasing, means we are making this bigger, bigger, bigger slightly. So if we increase the aspect ratio, the color will change this side. Similarly, if you coat with this, you will see different color. So all are well described in literature. And so we can tune the wavelength. We will able to tune the wavelength, because during bioimaging for any optical purpose, we want particular wavelength to where we can imaging, or we can combine with this optical emission with the particular part of the body where that's going to match with the wavelength. So that's or tunable wavelength of gold nanoparticle. Now this also how they grow, right? This is the growth nucleation growth particle. Unless it has to grow, any particle has to grow, they must be RC. They RC, which is this is ratio. If they are below that, they will dissolve. So there is a critical ratio. Above that, very important, because at critical ratio, the energy will find delta dg will be this much energy required to grow. And if the star RC is below this, they will redissolve. So this is well described, old theory, and how the particle grow. Initially, like the small particle takes the another bigger particle, take the smaller one on the surface. That is called Oswald ripening process, and that is the way of increasing the size of particle. So let's say we have a 20 nanometer particle, and we are in the during synthesis we produce, and we are adding the same seeds for 10 nanometer of the same particle. They will just generate on the surface. They will consume by the bigger particle. Same way, like under the big tree, small tree cannot grow. So they takes the energy from there. So all small particle have high energy. They will transfer, and the bigger particle keep going. This is called Oswald ripening process. So small one will combine on the bigger surface, and they will keep growing. And this is the iron oxide nanoparticle. As I said, FDA has already approved them for the MR imaging purpose, and they can be used, but and they can also produce a different size that we can produce, and we can use for the synthesis of the nanoparticle, and they are already been approved for that. And the basic thing is that what I said, the magnetization is very important, because when we are saying higher magnetic moment, the higher the magnetization, we can generate more T2 contrast. Overall, T2 contrast is very much important to generate lots of contrast. T2 contrast, I'm saying, not the R1. T1 is more depend on the surface phenomena. So if how fast the something comes to the surface of the particle and get transfer the energy, get relaxed, and that when energy is measured as a signal. So for the T1 purpose, the magnetization is not important. Number of free electron, total number of free important, but for T2 we use overall magnetization. So if iron oxide nanoparticle of, let's say, octopod, it is 30 nanometer size, they have magnetization around 600 EM relaxivity, right? So magnetization is around, say, let's say it is 60 EMU per gram. For this 80 EMU per gram, for this much magnetization, the relaxivity found for that is around 700. R2 is 700 per millimolar per second, because they are normalized under the concentration. So this is reporting in the form of concentration. So for different purpose, if you take a smaller particle, there is variation in the magnetization, because number of contributing ions are lesser in the smaller size particle. So if your particle is 16 nanometer, 30 more particle number of ion, so higher the magnetization. If they are 16, number of ion involved in making 16 nanometer particle are less, so they have less magnetization. So certainly the relaxivity will be less. Similarly for 10, it's small, but it's also depend on shape and size. So it's possible that certain size of very small, maybe 10 nanometer, can have high magnetization. That will also have the higher relaxivity. So we want to inject for the dose for in vivo application, particularly we want smaller with high magnetic moment that can generate lots of contrast. We don't want to inject lots of nanoparticle. So that's why shape becomes very important. Because everybody can be injected smaller dose where number of ions contributing in that particle is less, and that can able to produce lots of contrast. So this is the for octopod 30 nanometer size. I said 700 nanometer. If it is spherical particle of 16 nanometer size, they have different around 100 nanometer reflexivity. For iron oxide, this vary for different element, different oxide, different fluoride, different way. If it is octaford of 20 nanometer, they have 200 per millimolar per second reflexivity. So that's how it is. And now, if we check the reflexivity, different size particle, this also depends on magnetic field. As I said, the higher the magnetic field, higher the relaxation rate, and because the change in the alpha beta state will be large, so they will relax. Relaxation energy will be high, and better the contrast. So here, this is the basic formula to calculate the relaxivity from the relaxation time. I said that if you divide relaxation 1 by t is the relaxation time, how much time it relax. For the water molecule in our body that relax at the rate of T1 is 3600 milliseconds. Water in our body, that's relaxation rate is 300 milliseconds, 3600 milliseconds, and for T2 it is 3800 milliseconds. So any water is there, that's the same relaxation time. So we can convert the rate also if we are adding some contrast agent. From here we can find how much concentration of the metal ion. This is the contrast agent. Concentration of the contrast agent is M. So, and T1 is the relaxation time. So we'll find the relaxivity. So here, again, the same thing. If 20 nanometer iron oxide nanoparticle is there, then we'll size the relaxivity is around 700 per millimolar per second. And if they're 28, the still nearly slightly less. So depend how the shape, size, how much function, all are there. If 32 is still less, so all we can find from there. This would be a little bit higher, but some surface coating is also there that will change the size, because core size is 22, so they have higher. Core size 28. This must be the highest for this one, 32, but they have different. Because how much the iron oxide will not go directly in the body, we have to functionalize that. And that will that's what is on surface, how this contributes, how it's relaxed. That's a parameter. So this is the principle I'm saying, alpha beta state, right? So we change the energy. We usually when there is no magnetic field, all the particles are aligning in their own direction. But when you apply the field, then when in magnetic field, they will align either alpha state, either beta state. Depending on how much energy they have, they will align with that. Now we'll apply the radio pulse to push more from here to top. And when we switch up the pulse, they will come down, that energy will be measured. So this is the basic principle of NMR. Initially it was invented by physicists. So they said that radioactive, they use the terms radiation, but nuclear, they use the terms nuclear, but that was removed later, as I said. And so this is the phenomena. Why the more contrast? Because this energy change is directly proportional to the beta magnetic field. So that if you go on 7 Tesla, that energy difference here will be very high. So that's why this larger energy, greater the energy between this alpha beta state, and that energy will, when they will switch up the pulse, will get more energy and higher the contrast. So this is for the iron oxide nanoparticle. Also, core cell structure has been generated for both T1, T2 contrast. So iron oxide based core cell for multimodal imaging, they tried this one also, but as I said, this is not very fruitful because this iron oxide quench sometimes. The luminescence for this, the luminescence, they have quenching tendency to optical emission. They absorb the emission, so the contrast will not high. That's why the plan is to move from this core cell to lanthanide based or rare earth based nanoparticle for core cell imaging, where all set up, because these are the core cell from lanthanide. Yttrium is lanthanide, gallium is lanthanide, YB is lanthanide, ER is lanthanide, all are lanthanide. So if this part is also lanthanide, that will be best lattice match, and that will better the emission. So this is done in the setup, like if we have to give an IR light, 918 nanometer laser light, diode laser, or whatever the laser source is there of 918 nanometer. So that will excite the YB, and that Y will generate the energy to TM, that will red emitter, and this will also give the green emission from erbium-3. So this can also be used to, so for this setup particle, we can use the MR contrast. So here we can generate MR contrast for this core cell structure. So how we work with the lanthanide to produce the contrast. So basically, for this material was synthesized with 1 millimolar of dysprosium chloride. Dysprosium is a rare earth. You add water. In that required amount of water, need to add oleic acid and octadecene. So oleic acid and octadecene are surfactant. You added all the material under vacuum. You heat it 130 degrees centigrade. So they will convert to oleates. Dysprosium oleate will form, and this oleate will be there, and you cool down it. You just cool down and remove the vacuum. All should be removed. Cool it down. Add in this sodium hydroxide, ammonium fluoride in the methanol solution, and mix for 1 hour. Once they are mixed properly, 1 hour, sometimes you can go for longer duration because this is a room temperature. So you can mix for 2-3 hours, doesn't matter. Because you are mixing cooling at room temperature, and then you are adding all this at room temperature and then mixing it. Then you have to heat it at argon flow from one side, because we have to go in inertial atmosphere. And when this is a syncline setup. This is syncline setup. So we have to connect with the tube, and this also argon come from one side, going from other. And then once it is heated, so we'll heat it, and they will at 300 degrees centigrade with oil bath. So that will leave the sodium dysprosium fluoride nanoparticle, and dysprosium is T2 contrast agent. So if you add it, and then we'll get this nanoparticle, wash 3-4 times and centrifuge that, and you'll find this nanoparticle. So this is a machine for scanner, right? So as I said, that if we are early stage, then we need a contrast agent, because this machine will not able to detect between healthy cell and cancerous cell. If you are later, second, third stage, possible that this can detect. So whole idea is to extend the life by 10 years or so. If we use the contrast agent at early stages, 10 to 15 years is good number of life to, if somebody can extend. So here the setup. So that's why the idea is to get contrast. At the moment, we are using gadolinium-based contrast agent, mostly complexes. So how this measure getting the T1, T2 relaxation rate we are measuring. The magnetic field, as I said, when our nanoparticle are here, and we don't apply field, they have random orientation. As I showed in the last figure, they have random orientation. But when we applied the magnetic field, all the metal nanoparticle will align around G-axis. Along the magnetic field, they will align. Now this is the precessional frequency omega. When we apply a radio pulse, we will bring this G-axis along XY axis. With the radio pulse, we apply, and it can give, I think, 90 and 120 degree pulse. This RF pulse is there. So we'll bring all the magnetization in XY axis. So we'll bring it here, and we'll switch off the pulse. When pulse is switched off, this try to gain its original position, because this came through the applied energy. It came in XY plane, came through the applied energy of radio pulse. So when we switch it off, it'll go back to its normal position, and that's measured. The gain is signal. Now this is going back to G-axis. So its gain is magnetization is. So it is going back. So gain is magnetization is T1. This is a gain is magnetization. We're talking. So this is T1. Right? Getting gain. Magnetization is getting increased from here. And if you are bringing in this direction, that is T2. So we are bringing here G to XY plane. That is T2. When you leave it off, switch off the pulse, this will try to go back here. So this gain is magnetization is T1. This already published in Journal of Metal Chemistry B, and I think Quantum Chemistry also, this picture is there. So this is a principle of how we change the, so from same, by switching the pulse, by changing the both particle can give T1, T2 both relaxation time. Usually machine provide both. So we measure both. We find T2, we find T1, from where we get whether the particle is T1 based or T2 based, depending how much it is able to short the time of water proton in millisecond. So as I said, this is T1 is around 36 millisecond, and this T2 is around 3800 millisecond. So let's say by applying this measurement, by applying using contrast agents, we measure for a particular contrast agent. And this we find really shortening. T2 we short it to up to maybe 4 millisecond. So that material will be T2 contrast. How much getting shortened? depending on T1, T2 measure time. And this is the magnetic moment of the lanthanide, and you see here how much it is. Why we are using gadolinium? Gadolinium has already 8 EMU. This is magnetization of gadolinium, Bohr magnetron. So this is gadolinium is already 8 Bohr magnetron, and highest is dysprosium. So dysprosium and holmium both can be used for T2 contrast agent, because the gadolinium has highest number of unpaired electron. One more parameter is that 1E, they call it, or TE, that is used for, that is how fast, that is not overall measurement, but that change, that gives how fast this change the water coming to the surface of particle and get relaxed. That is also called resident time too. So this, why this is T1 contrast, is because there is resident time. So if it is coming on the surface, this should go there, this should not hang up there. And this T2 is the overall measurement. This is resident time on the surface of this, very short. That's why I think a number of large unpaired electron, which is 7. That's why this is used, gadolinium uses T1 contrast agent. So it is a higher number of high magnetic moment for this one. Is this 10.2 mu b, and but both, this is also 10.2 mu b, where for the gadolinium it is around 8 mu per gram. So this is a T1 base, this is T2 base. But for T2, the overall magnetization is used. Like how much EMU per gram is there, how much total number of magnets, because for the gadolinium based contrast or any material which is T1 base, so we said that only surface atom contribute because they are close to the surface, and the water molecule has to come to the surface and get relaxed. So any T1 based material is there, that's more surface phenomena. But T2, if it is there, that's overall, how much overall magnetization. Overall magnetization is not important for T1 based contrast agent. That is more how many number of electron are there and how much the resident time, how fast is come to the surface and get relaxed. So this here it's more clear here. This is resident time. Tau star is a resident time. So if it is coming to the surface, this would relax. Should not hang there. It comes and relax. And T1 is more outer sphere phenomena. If you are saying T1, this is more outer sphere phenomena. So if molecule will come to the surface, both the process has to relax the hydrogen proton or the water molecule proton or the fat proton in the body. We are generating the contrast in the body by relaxing the fat proton or the water molecule or other part of the body which has the hydrogen. So they relax. So both, this is a, if you see here, the T1 is more outer sphere phenomena. They will come relax. But when we are using T2, that will be more overall magnetization. How much total magnetization is there? But any material both has T1, T2, but one dominates. For gadolinium, this is the T1 dominates. For dysprosium, it is T2 dominates. So, but the phenomena is still same. Both will come and relax. This is the outer sphere. This is inner sphere compressed. This is two part. And this is rotational time, tau r. It has to rotate. If it is rotating, that might increase the relaxation time, because the phase which bind water is moving from here to other place. So this rotation is also important. Of that, the contrast agent rotation time is also very important. If it is not rotating, is just one place hanging, might possible that can increase the resident time. So this keep rotating and they keep moving because a certain amount of energy will change. So this is the basically this is the model which tell how we can generate. Either if we are making T1 based contrast agent, so we'll most focus the T1 shortening contrast nanoparticle on the surface. So as I said, our plan is to make multi-model imaging where we can use both T1, T2 model for MRI imaging to get more accurate results, should not be misleading. So if it is both T1 based MR imaging, T2 based MR imaging, that will be more concrete answer. So of the result. So here, if you see, this is the T1 based contrast, we are saying sodium gadolinium fluoride Iron oxide nanoparticle of smaller size also work as a T1 contrast agent. Very small nanometer size, 5 nanometer. They work as a T1 based contrast agent. Where high one, 20 nanometer or 15 nanometer, they work as a T2 contrast agent. So here we are keeping gadolinium is always T1 contrast agent, because for this T2 shortening time is very, very less. They don't decrease much time of the water molecule or hydrogen proton. So here they will coat this gadolinium on the surface, and we are keeping dysprosium, sodium dysprosium fluoride core or sodium holmium fluoride core. Both has magnetic moment for one atom 10.4 mu b. So number of if ions are 100, then we'll multiply by that. So that will very, very high mu b, Bohr magnetron. Here, this is one way. So we are saying here the part, if this concrete structure, these are not porous, but if we can make somehow this green, which is sodium dysprosium fluoride or sodium holmium fluoride, as a porous structure, where the T1 molecules should be inside those pores and water is still able to access those pores. If they are unable to access, then T1 will not find. So this is a kind of porous structure where we are keeping this cell material within those pores, and the porous structure water molecule can reach there. If they're reaching there, we'll still see T1 based contrast agent, and T2 is over our magnetization. So T2 has no problem. Will find the, or if higher the overall magnetization, better is the T2 contrast. So we can see from both model, this both structure can work as T1, T2. There can be many more design, depend how you are designing. Some other can be also possible. So either this or this structure is possible. So, so we are saying the up conversion nanoparticle mostly because our plan is to dope something. We can dope in gadolinium fluoride. So we can use T1, T2 as well as optical imaging, three modal contrast agent. We'll dope something luminescence here, and we will get the contrast from optical imaging also together with T1, T2 contrast. So here mostly the plan is to make them up conversion. So up conversion, when we're saying that we are using low energy molecule and producing high energy molecules. So that is a up conversion process. So if you are giving 980 nanometer wavelength, that is longer wavelength, low energy, generating shorter wavelength red or green. So we can image, the optical imaging is also possible by doping the sodium gadolinium fluoride with this setup, YB, TM, ER. If you are doping only YB, we will get red emission. If we dope this green, depending on which part we want to imagine, if there are some protein which generate green, then we can go with red one. If there are some other red something molecules, we can go with the green one in the body. So it's possible to co-dope either this, or both can be co-doped. So in the same gadolinium fluoride structure, we will be able to optical imaging as well. And this is energy. This diagram is well known because from literature, how the energy, how the emission comes. So we can see emission from these one, like gadolinium has this white. So there is energy, so a long energy gap. So we see emission, but not like they lack. Still, it is lacking. And so best emitter are erbium and thulium. So this is thulium. You can see the fixed energy level here. Erbium is also emitter, so energy level. Dysprosium is not very good emitter because this is a continuum type structure, not much gap. Same for gadolinium also, but gadolinium does have some emission. So this is the particle prepared. The particle we prepared, like same particle we prepared for different size, and for we prepared sodium dysprosium fluoride nanoparticle, like here 5 nanometer. This we prepared for 10 nanometer. Here also 20 nanometer around, or maybe slightly 15 nanometer. They are longer here. So 5, 10, and 15. They are capsule size shape. Shape is just like capsules, and so they have different aspect ratio. They also prepare. They are very hard to control sometimes, but they are there, and we can prepare a different size, and we can measure all this result with the XRD whether they are those particle or not. So and this is a core cell structure. If we coat this particle, this core, and this is a cell, so we'll see different type of core cell structure of nanoparticle, because future idea is that we can keep this core and make this core cell where we can co-dope with erbium and thulium. So we can do T1, T2 model imaging in MR and as well as optical imaging as well. So this is again for to check like different. So here we try to see how much reflexivity is there. This is my published paper, I think JPC 2017, ACS publications, very good article. So here, why we, if you keep, they have different relaxation rate. Where diamagnetic particle do not relax in the magnetic field, but this is paramagnetic, so they relax. And we have it's shown here, if we are keeping certain thickness of dysprosium, how, let's say 2 nanometer thick dysprosium on surface of yttrium, how much the contribution is there. Or we are keeping again Y and 4 nanometer thick dysprosium on surface, so how much relaxation rate is there. So all have been measured in this article. And that shows how, because ultimately for imaging purpose, we have to see relaxation time of the water molecule, how it's relaxing. And this extra diffraction shows the particle prepared 5.6 nanometer or some other where 10 nanometer previously I showed, 20 nanometer or 22 nanometer core cell structure. So this is prepared. And okay. And the prepared nanoparticle has the highest magnetic moment. As I said, the larger, bigger the size, greater is the magnetic moment, because number of contributing ions are more in 20 nanometer size particle. This is 10 nanometer, half of the particles, half of number of ions might be half or slightly more than half. So, and if they're 5 nanometer, they have even less number of ions, so the magnetation will vary. A highest is for 20 nanometer size particle. Then we'll see and measure that. And this is how we have to functionalize, because they have oleate on the surface, right? Oleate is hydrophobic in nature, so we have to make it hydrophilic. And then we also measure the size of the particle in a water molecule, because ultimately they have to go in PBS solution, PBS buffer solution, or water or blood pool. So they have to be like dispersible there. So their surface is modified with the hydrophilic polymer on the top of the surface. Initially PMOPG was there, then we coated with the hydrophilic polymer on surface. And the particle prepared, you can see the particle were around, average size were 14 nanometer for these particles. And then we also measure the relaxivity for that. So measure relaxivity for those particles, we measure at 2 Tesla, 9.4 Tesla, at 3 Tesla. As dysprosium, this is mostly for dysprosium particle, because we use this only for the imaging purpose at the moment. And the lab is still doing some work at there by the multimodal imaging and core cell structure. But we, during my stay, we did only this one with dysprosium T2 contrastion. So as I said, if you use the higher magnetic field, the relaxivity is higher. And for as dysprosium is T2 contrastion, so we will say large change here for T2, which is transverse relaxation rate. Longitudinally, there is not much change, because this is more surface phenomena. So this is more change for gadolinium, not for dysprosium. This is T2 contrastion, so we can see large relaxivity, which is very much important for the contrastion. So this is very high we got compared to the commercially available contrastion. This is well high, very, very high. We got around the relaxivity for this 9.4 Tesla, we got around 120 or so. So this number is very, very high compared to the commercially available contrastion. Look at here. If we size of 20 nanometer particle, R1 for one dysprosium is 101. This is for one dysprosium man we are measuring. So this is 101. If you go per nanoparticle, this is very, very high, 6,479. And the ratio, the specs R2 by R1 with 306. And if we compare with the commercially available contrastion, which is Feridex, Rezovist, so this number is very high. This is 306. The commercially available contrastion only 22 or 31. So this is very, very useful for the application for imaging purpose. And then we study the toxicity with this nanoparticle also. We injected in the mouse model, in the mice, and we studied basic toxicity issue with this nanoparticle, not the with the blood sample or that. We injected the particle, tail vein injection, and all the organs were taken out. Their behavior were monitored, and during those period, and digested in aquaregia and taken out, and we study how much they are in each parts. So this is the behavior. The normal, they behave very normal. How much got injected respect to the weight. mouse weight in kg. And mostly as you know, this all goes in reticuloendothelial system. RES system is there. They absorb most of the particles. So we still have to something designed that can stilt the RES system, because they are the most one to absorb. So we have to we have designed some model or some surface coating that can stilt these RES system. So mostly at the moment PEG is the best still. PEG can still the RES system. If you coat this particle with PEG, they can go more in other part of the body. But here with this polymer, we are able to get very less, even very less in the brain. Almost nothing is there, because these particles are bigger size, very hard to cross blood-brain barrier. But mostly the liver, anything goes, we take almost immediately taken by the RES system, the reticuloendothelial system. So you can see here liver is taking 63.4%, and spleen is 0.8, rest is another part of the body. So some designed PEG, if you coat with PEG, they will still this RES system, they can go to other part of the body. Okay. So these particles were injected in mice model, one mice, this is bulby C J mice and bulby C mice, and at 9.4 Tesla, they injected around 58 mg per kg of mice weight, and we imaged the T2 weighted MR imaging because we injected dysprosium. So you can see the signal. This was generated tumor, and this tumor is contrast. We still can see this is darkening. It's T2 contrast. So this is gone. This whitening. So here we can say T2. But to get more concrete information, we also go for T1 based. If we are using T1 compared to this whitening, that T1 this will be even whiter, because we are using this time T2. If you are not using this sodium disulfide, instead of that we are using gadolinium, that will be giving more whitening contrast here compared to this tumor area. So either both model we can use, dysprosium on core, and cell is the gadolinium based contrastion. So one time we'll see compared to this T2 will be darkened, and when we are using T1 compared to this whitening, that will further whitening. So this is just imaging after 10 minutes, and then still there is darkened compared to this one after 2 hours, but after 24 hours we believe that the particle moved out from there, so this become more whitening, get to normal position. So the conclusion we have, synthesized the oleate is in the past synthesized these nanoparticle, and size were varied, and we measured the concentration, highest for the bigger nanoparticle, then surface was coated, and then we image that particle and we'll find decent contrast. So preliminary imaging results of the mouse with the brain tumor showed some improvement after 2 hours. So this can be used in the past, can be further taken care. So future work can be like, as I said, we have to design something where they can stilt the RES system more, reticuloendothelial system, which include liver and spleen. So the particle will not be taken by the liver spleen. By proper designing, keeping some molecule that can still this. So if we coat this nanoparticle, PEG1, polyethylene glycol is the one that stills the RES system. So we can coat with that, or we can use these particle to dysprosium fluoride or gadolinium fluoride for both this one diagnosis. And so this can be used like to facilitate the target specific delivery nanoparticle. We still can use antibody, surface coating, all can be done. So these are the thanks to my postdoc supervisor and this group who performed that MR imaging is from Calgary, Canada, and my earlier collaborator, University of Oklahoma, USA. Thank you.
Thank you very much, sir.
Yes, thank you. Welcome.
Participants, if you have any questions or queries, you can ask now. Participants, you can ask questions.
You're welcome. Lots of need to do. Yeah, I can getting some message. Lots of effort needed from us. If anyone has question, ma'am, they can reach me through mail also. I can help, no issue.
Okay, okay, sir.
They can reach me mail because I have extensive synthesis and paper also I'm still writing because I'm an R&D support at Malla Reddy University.
Okay,
And any trouble during synthesis here, there, I can help. No issue.
okay, sir. So we conclude here today's session. On behalf of organizing committee, I extend our sincere gratitude to our esteemed speaker, Dr. Anurag Gautam sir, for delivering an insightful session on MRI imaging and its analysis. Dr. Gautam clearly explained the principle of NMR, providing a strong foundation for understanding MRI technology. He further discussed MRI imaging and analysis, including nucleation and growth process, iron oxide nanoparticle, and upconversion process. His presentation of in vivo results and insights into future research directions added significant value by connecting current research outcomes with upcoming possibilities. We truly appreciate Dr. Gautam's valuable time, expertise, and clarity of presentation, which made the session highly informative and beneficial for all the participants. Once again, we thank Dr. Anurag Gautam sir for his meaningful contribution to this FDP.
Yes, welcome, ma'am. Thank you. Thank you.
Thank you, sir. Thank you very much. One notice to all the participants. On your Atal FDP participants portal, you may get the link for test. So tomorrow after FDP is over, you have to go through that test. If your attendance is 80% and your passing mark is above 60, then only the certificate will be generated by the Atal FDP.
Ma'am, test will be conducted tomorrow, right?
Yes, sir.
Okay, ma'am. Okay, thank you.
So link will be open for 24 hours or for tomorrow only, ma'am?
Madam, link is activated now and it will be there until 12 midnight, tomorrow 12 midnight, which is
Okay.
the last date of our FDP.
Okay, ma'am.
Any other questions or queries you can ask?
And the link will be available in Atal website, right?
Yes, on Atal FDP participants portal.
Okay, ma'am. Thank you.
Yeah.
Ma'am, that link will be activated after tomorrow's session will be over, right, ma'am?
No, sir, it is activated now. But
Oh,
my suggestion is after completing all the sessions, you can appear for that.
okay, ma'am. Thank you.
Yes.
So, ma'am, can we leave now?
Yes, sir. Yes, you can.
Okay, ma'am.
The session is over. You can leave now.